So today we are going to be talking about, we're starting a new unit. Of course, as with every unit in chemistry, you don't get to just forget everything you learned before because it's all going to keep coming back. But this is a new topic. We're going to be talking about moles. Not the small furry creature, but the unit of measurement in chemistry. So we're going to talk about why we do this, and we're going to pay attention, unless there's an emergency, in which case you're going to let me know, okay? And I'm going to move the Zoom thing. I'm trying to have Sophia on here on the Zoom, see how to make this less obtrusive. How about over there? Yeah, that'll work. Okay. So, there are words that we use to indicate a specific number of something. A pair. If I have a pair of socks, how many socks do I have? 2. If I have 4 pairs of socks, how many socks do I have? 8. Okay, good. That was a little slower, it's okay. Brain's warming up here. If I have a dozen eggs, how many do I have? If I have 3 dozen eggs, how many do I have? 36, yeah. So I can use the word a dozen to talk about anything. I don't have to talk about a dozen eggs. I can say I have a dozen socks. And that means I have 12 socks. Which means I have how many pairs of socks? 6. I have 6 pairs of socks, right? So we can go back and forth between these different numbers that mean something, that mean or these different words that mean a particular number. So we talk about a dozen eggs, I can talk about a dozen pizzas. If I am buying paper, I might buy it by the box, but I might also just buy it by the ream. A ream is one of those packets of copy paper that you see, and there are 500 sheets in a ream. So all of these names, a ream, a dozen, a pair, they all mean a particular number, but we use them because they're more convenient. It is much more convenient for me to say, I'm making a bunch of quiches, can you go get me 3 dozen eggs from the store, than for me to say, can you go get me 36 eggs from the store? It's just, we just think better about things in quantities like that. Now, when we're talking about atoms and molecules and chemical reactions, we can't, these things are very, 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 very small. Can't see them. I can't pick up an atom with a pair of forceps or weigh out one atom on a balance. I can't see one atom or one molecule reacting with another molecule. In fact, I could put 1,000 atoms together and I still wouldn't be able to see it or pick it up with a pair of forceps. I could put 1,000,000 atoms together in a little ball and I still wouldn't be able to see it or pick it up with a pair of forceps. That's how small atoms are, okay? So if we're talking about actually doing chemical reactions in a lab, and we're talking about quantities that we can actually measure out or pour out or manipulate and actually see what's happening, we have to be talking on a much, much, much bigger scale than a single atom or even a dozen atoms or a ream of atoms. That's not big enough for us. So we have to come up with another solution to talking about manageable quantities of atoms and molecules, which is the slide that I just skipped over. And that solution is what we call the mole. And it's spelled just like the name of the small furry creature, hence lots of science jokes about moles and like the shirt I'm wearing. It's just like a dozen or a gross or a ream or a pair, but it's a totally different number. It's 6.02 times 10 to the 23rd power. That is a really, really, really big number. This number is written in scientific notation, and in a little while we're going to do some practice with that. The scientific notation is great for allowing us to work with very, very, very big numbers and very, very, very small numbers. So if I were to write out this number, it would be that's how many atoms are in 1 mole of a substance. Okay? This is a huge pain in the butt to work with, and you can't even type it into your So that is why we shorten it into scientific notation. But it's such a big number that because the atoms and molecules that we're talking about are so small that we have to have a ridiculously huge number of them in order to even be able to see them and work with them. So where does this particular number come from? Why, a dozen kind of makes sense, a ream kind of makes sense. It's a nice whole number. What is this 6.02 and why is it 10 to the 23rd and not 10 to the 20th or something like that? Where did this number come from? Well, it has to do with the number of atoms in exactly 12 grams of carbon-12. That's how it was determined initially. Why did we do it that way? Well, it's easier if we can use the same numbers to talk about the mass of a substance as we use to talk about the mass of a single atom. So if I have one carbon atom, we know from the periodic table that I have about 12, each carbon atom is about 12 atomic mass units. I seem to have lost, here's the periodic table. So we've been talking about the second number, the other number on the periodic table, in terms of the mass of a single atom. And we talked about how there's decimal points there because there are different types of carbon atoms, different isotopes, and this is a weighted average of all the isotopes of carbon. But we've still been talking about it in terms of the mass of one carbon atom. But it turns out, if we set our quantity, the mole, to this number, 6.02 times 10 to the 23rd, we can also use these numbers as the number of grams that 1 mole of the substance weighs. So 1 mole of carbon weighs 12 grams, just like 1 carbon atom weighs 12 atomic mass units. So we get to use these numbers on the periodic table again, but now talking about much bigger quantities that we can actually hold in our hands. So our mole is equal to 6.02 times 10 to the 23rd particles, which I'll talk about that in a second, which for carbon, if we have 6.02 times 10 to the 23rd atoms of carbon-12 specifically, because it matters what isotope we have, then the total mass of that is going to be 12 grams. So we can go back and forth between the periodic table and the mass that we can see on a scale, on a balance. That is why we use this funky old number. So it's called Avogadro's number because this scientist, Amedeo Avogadro, did a lot of the work on quantities and volumes and masses of gas particles for many years, leading up to this decision to make this number what it is. So he actually did not discover it or invent it. It was named after him because so much of the work that led up to the invention of this number was work that he did or participated in. And if you ever go to Trader Joe's, they have Avocado's number, the guacamole, and it's a play on words on Avogadro's number because it's moles. So if you didn't get that joke before, now you do. Okay, so this is the number of particles in a mole. And I specifically write particles here because it can be anything. I could have a mole of eggs. That would be, we could pretty much coat the earth with a mole of eggs, okay? But I could have a mole of eggs. I could have a mole of pizzas. I could have a mole of anything. In chemistry, a mole can be talking about generally one of 3 things. Atoms of an individual element. So the whole story about carbon, 6.02 times 10 to the 23rd carbon atoms in 12 grams of carbon. We can also talk about molecules. We can talk about having a mole of water molecules. That would be 6.02 times 10 to the 23rd molecules of water, each one of which had 1 oxygen atom and 2 hydrogen atoms. So now we're talking about something a little bit bigger than a single atom, but still something that we're not going to be able to see or pick up with tweezers until we have a whole lot of them. And then the other thing we can talk about is formula units, because remember that our ionic compounds don't really make discrete molecules. They make these big crystals that have a ratio, which gives us our chemical formula between the positive and negative ions. So if we're talking, the equivalent of molecules in ionic compounds is formula units. So we could be talking about any of these when we're talking about a mole of something. We'd be very specific about it. Okay. So a couple more mole facts. If you had a mole of pennies and you put them in 6 stacks of pennies, they would reach 300 meters high. So that's a lot of pennies. I certainly don't have that many pennies. I might on some level. 6.2 times 10 to the 20. No, I don't think I do. I'm not even close. And then, but at the same time, when we're talking about things that are so tiny, like a molecule or an atom, 1 mole of water, 6.02 times 10 to the 23rd molecules of water, is only 18 milliliters, only about a tablespoon. So a tablespoon of water has about a mole of water molecules in it. So when we're talking about really small things, we have to be using these huge numbers in order for them to make sense. Yeah, Liam? No, that is the number. That is avocado's number, 6.02. Well, 6.022 something, something, something. It's it extends out a little bit, but we usually just use it as 6.02. But again, that is tagged to the number of carbon atoms in 12 grams of carbon. And that allows us to say that's also the number of hydrogen atoms in 1 gram of hydrogen. It's the number of argon atoms in 39.95 roughly grams of argon. Okay, so we can use all these numbers on the periodic table as a mass per mole of that element by using 6.02 times 10 to the 23rd as our conversion factor. Does that make a little more sense? Okay. All right. So when we're working with these numbers, and we will do a little bit of work tomorrow with Avogadro's number and converting back and forth between particles and moles, we have to use scientific notation, because otherwise it would take forever to write it out and our calculators can't handle it. So this is how scientific notation works. This should be a little bit of a review because we should have covered it at the beginning of last semester, but that was a long time ago. So that's why we're doing a little bit of review today. So here's how it works. Any number that is in scientific notation has 1 digit before the decimal, just the ones place before the decimal, and then however many digits after the decimal that you need or have precision of in whatever quantity you're measuring or calculating. And then it's always times 10 to a power, to an exponent, because we do math in base 10, and so we're basically, when we're putting something in scientific notation, we're just moving the decimal point in one direction or the other. So it's going to be times 10 to a particular exponent. And that exponent can be positive or negative. And I'll show you how that works in a second. So always 1 number before the decimal point, however many afterwards that you started with, and times 10 to the something power. So if you look in the packet that you picked up today, there is a description. The first 2 pages are just a description of scientific notation in case you need to refer back to it, and a little bit about using calculators, which we'll also go over in a second. And then there's a double-sided page with some practice problems. I only need you to do one side, and I'm going to go through a couple of examples first. If you want to do both sides because you're still a little sketchy with it and you think you could use the extra practice, you can do both sides. It's not a whole lot. So if you look at the first page, it asks you to convert these quantities into scientific notation. So here's the first 2, and I'm going to show you how to do it by hand, and then I'm going to show you how to punch things into a calculator. So any number that I have that doesn't have a decimal point in it, where is that decimal point? Where is the decimal point for any number? Yeah. At the end, right at the end. So this number here has no decimal point. The decimal point is right there. Okay, so that's where it starts for this 35,920,000 number. Huge pain to write this into my calculator or to write it by hand. So to convert it to scientific notation, I have to move this decimal point until there's only one non-zero number before it. And then I'm going to count how many places I moved it. So I'm going to take this decimal point and move it 1, 2, 3, 4, 5, 6, 7 places. And what I'm going to end up with is 3.592. And I'm going to assume that these are not significant figures. You can just keep it to whatever the non-zero numbers are at this point. 3.592, and then I have to indicate that I moved the decimal place. So I have to say times 10 to the however many spaces I moved it, which was 7 in this case. This exponent is going to be positive for very large numbers and negative for very small numbers. So if I'm moving the decimal point to the left, it's going to be a positive number because I have I started with a big number. If I'm moving it to the right, it's going to be a negative number. Yeah? What's that? Right, exactly. So the second one, we're going to have to move the decimal point to the right because this is a very, 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 very small number. So we've got, let's see, thousandths place, millionths place. So we're talking like almost billionths in this number. So it's just really, really small number. Kind of a pain in the butt to count all those zeros and figure it out. So let's convert it. This time we're going to again count the number of places. 1, 2, 3, 4, 5, 6, 7, 8. I'm stopping here because I want one non-zero digit in front of the decimal point. So that's going to make it 5.27 and then times 10, and I need my exponent. The number of spaces I moved was 8. But it's not times 10 to the 8th, because that would make this a very big number, and we know it's a very small number. Yeah? It is exactly it. It is times 10 to the negative 8th. Okay? So when you see a negative exponent, you know, tiny, tiny, tiny. When you see a positive exponent, big, big, big. And make sure that it makes sense when you do your conversions, when you look back at the number you started with. Okay? So you can do, we're not going to go through the next two together. I do want to go through a couple of the calculations under number 2, because we are going to be doing some multiplication and division with these numbers in scientific notation a little bit. And so I want to make sure you are comfortable with that. And since I'm not expecting you to do it in your head, let's talk about how we do it with a calculator. So this is based on the calculators that I have in class, but if you have your own graphing calculator, especially if it's Texas Instruments, it should be very, very similar. If you have trouble finding the right sequence on your graphing calculator, you can ask me later. We'll have time for that kind of stuff. But I'm going to talk about how we enter these things into one of these calculators. So my question asks me to multiply 3.1, oh, sorry, that's 3 point, I miswrote it. It should be 3.15, not 3.5. Let me just fix that real quick. 3.15, that's a 1. And the other one is still 6.3. Okay, good. So to enter something in scientific notation on your calculator, you're going to clear everything out, and then you're going to start with the number, the base number here, the 3.15. You're just going to punch that in, 3.15, like here. And then you're going to go to this, You're going to go to this button because we're going to need to shift to one of the upper functions of the keys. So you're going to hit second, and then you're going to hit this key right here. It says x to the -1 on the button, but it says EE on the shift portion. So that's what we want. We want second, EE, that just shifts us up to the blue functions. And EE is how we say 10 to the something. In some calculators, it might say EXP instead of EE. So if your calculator has an EXP button, that's probably going to be the same thing. Okay? And then, so I'm going to put in second EE, and that's going to give me, on my calculator, it's going to look like, oops. It's going to look like this, 3.15 with a tiny little capital E. Okay? And that's now telling me that's the times 10 to the, and then I have to put my exponent in it. So in this case, it's 10 to the 6th, so I just hit a 6. Okay? So this is what comes out. I can hit enter if I want to just see what that looks like. I can also hit times, because that's what I'm trying to do. I'm trying to multiply these two numbers together. If I hit enter, oops. It's not going to let me, do that, is it? Oh, there we go. Oh, of course, because I did this. Hang on. Okay, so if I just hit enter here, then it comes out as 3150000, which is 3.15 times 10 to the 1, 2, 3, 4, 5, 6. So you can have it show up on your calculator that way. And I'll talk about how to switch back and forth between the notations in a second. So I've got my 3.15 E6, and I'm going to say times, and I'm going to do the same thing, 6.3, second, EE, 10. Oh, sorry, that's supposed to be a, oh yeah, I didn't change this one, sorry. Should be an EE4. I had different numbers here, and then I realized I should probably do the ones that are actually on your worksheet to make it easier. And of course, I didn't do it perfectly. So 10 to the 4th. Oops. Oops. All right. So if I did everything without pressing enter, I would have 6.3 little e 4 on my screen. And when I hit equals, give me a second because I just cleared this out by mistake. Four. I get an answer that is already in scientific notation, even if my calculator is not previously set up for that, because this answer has to be in scientific notation to be able to be displayed on the calculator at all. So this is 1.9845, and then you can see a little times 10 to the 11th power, okay? I'm not going to make you do these by hand. If you want to learn how to do this without the calculator, I'm happy to show you, but let's be real, we're all going to be using calculators, okay? So that's how I would enter things in the calculator. Now, if I have my original number, my 3150000, and I want to show that in scientific notation, here's what I'm going to do. I'm going to go second, and then I'm going to go to this degree button, which says sci-eng above it in blue. So I'm going to hit that, and that's going to give me a choice between flow, sci, and eng. Flow is just normal decimal format numbers. Sci is scientific notation. So if you move the arrows so that this is underlined and hit enter, then your number should come up in scientific notation on the calculator. So if I have a number, I go up to second, I go to DRG, which above it says sci-eng, And then I can toggle with the arrows back and forth between flow, psi, and eng. And psi is what you want for scientific notation. Flow is just regular decimal notation. Okay. One more thing. If you're dealing with a negative coefficient, the next problem asks you to divide 5.32 times 10 to the minus 6 by 1.8 times 10 to the 10th. So the negative, you have to make sure that the exponent is negative when you are entering it. So you use the plus minus key or the little minus in parentheses. Yes? What's that? Oh, okay. So then you would, let's see. Because you probably have, you probably go to format, I think. I'd have to play around with it a little bit. It's probably more, you probably have more of a menu. So you'd probably be accessing your menus on your fancy graphing calculators to switch between scientific and decimal. Okay? You are very welcome. Okay. So that is yes. Oh, yeah. That is a very quick tutorial on scientific notation. Again, you have some practice problems. I will post some keys to both of these pages so that you can see how you did. And let's maybe, let's see, how long? We have 45. Let's maybe break at 1:15 to do the Titan time lesson, okay? So from now until 1:15, you can be working on this. You can work on other work that you need to do for chemistry. You can finish a quiz if you have a quiz that's unfinished, or take a quiz if you have a quiz that you haven't taken. I'm happy to work with you on chemistry stuff, however you want to do it. If you have everything done in chemistry, nothing to take or retake, and you have other stuff to work on, then please go ahead and do that. Yes? What's that? Oh, yeah. You can, if you're looking up something like how to use your personal calculator, you can look that up on your phone at this point. Yes? So it gives you the answer not in scientific notation? Is that what you're saying? Okay, yes. Sure. Yep. That should be fine. And then, yes, you can either write it out as in the decimal notation that it gives you, or you can convert that decimal notation to scientific notation by using that process, going to flow, psi, eng. Okay. Are there any more general questions not specific about specific problems? Yeah. Oh, yeah. Okay. All right, I'm going to stop the recording.